Welcome to the MIA course module titled Utilizing Radar Data for Storm Environment Analysis. This short module in the MIA course aims to help you learn about how WSR-88D radar data can be helpful for assessing near-storm environment change and the hazards such change can support, as well as learn about the limitations of 88D radar data for the purpose of near-storm environment analysis. This is a more advanced level module because it deals with a more challenging topic. The environment changes we can infer from radar data will likely not appear in the SPC mesoanalysis page or on NWP analyses. The mesoanalyst needs to mentally adjust small-scale environments based on an interpretation of radar data that may or may not be accurate. There are two primary uses of WSR-88D data in severe weather operations. First, storm hazard detection and motion, which we use in a reactive sense to issue warnings. And second, near storm environment and storm influence on environment, which we can use to proactively try to anticipate the first item, hazard detection and motion. Our focus in this module is the second bullet. Is this statement true or false? The WSR-88D is limited in its value for providing near storm environment information. Well, unfortunately, radar is somewhat limited in its value for environment analysis due to a number of radar-related issues, which tend to make it most useful in areas relatively close to, say, within 50 miles of the radar site, with much less value at longer distances from the radar site. Let's review these key radar issues. Take a moment to think about the issues that exist with radar operations and the resultant data that could influence your interpretation of the data. Consider height and width of the beam, how much coverage in the atmosphere you're getting, and orientation of beam radials to the features of interest. There are a number of issues associated with radar operations and the data provided by radar. Here is a list of 5 that you likely learned in radar training, but I will briefly review here. The first one deals with beam height and width, and how they change with distance from the radar site. This can result in a difference between what the radar shows to exist and what actually exists. Averaging of data within a widening beam, the height of the beam which can overshoot distant lower level features, interpolation of data between elevation slices, and the lack of any extrapolation above the highest data slice all can negatively impact your interpretation of the data. That negative impact increases with greater distance from the radar, and also occurs near the radar within the cone of silence. The impact of this can be seen at times when looking at 2 different radars at 2 significantly different distances from a key target. Each radar could show a different result, which can confuse the warning forecaster. Consider, for example, strong low-level rotation, which the Knoxville, Tennessee radar would detect here, but the distant Birmingham, Alabama radar would overshoot. Thus, one radar shows strong rotation on its lower slice, while the other radar does not. Here's an example. Take a look at the reflectivity cross-section to the right for a storm about 60 miles away from the radar. What are we seeing? Is it a weak ecoregion associated with a developing supercell? Or are there 2 cores next to each other, one mature and one new core that is elevated, that are averaged within a widening beam to suggest one large core? The radar issues that exist can make accurate interpretation tricky at times. Beam refraction results from the environment the radar energy is traveling through. A dry adiabatic layer supports slight subrefraction of the beam, while an inversion, be it near the surface or associated with a cap aloft, supports slight superrefraction. Normal beam refraction, upon which the radar heights of features are based upon, rarely ever exists in a thunderstorm environment. Thus, 3-dimensional features and structures shown by radar are rarely perfectly accurate. While superrefraction or subrefraction tends to be quite small, its impact on beam height quickly increases with distance from the radar site. So the impact is likely small within, say, 40 or 50 miles of the radar, but can grow quickly as you approach 100 miles from the site. When looking at 2 different radars about the same distance from a given storm, with one radar in the unstable environment ahead of the storm and the other within heavy rainfall from a different storm, the difference in terms of refraction can lead to substantial differences in storm appearance between the 2 radars at nearly the same time. Talk about confusing to the warning forecaster. Radars may not operate at exactly the same power. Sometimes they may be on the warm or cool side. Here's an illustration from the Southeast River Forecast Center showing bias based on accuracy of radar estimated rainfall. Note adjacent warm and cool radars across the Florida Panhandle. There could be some impact on interpretation, though the level of impact is usually not known during the event. The VCP utilized can affect interpretation. The more slices you have, the more accurate your three-dimensional storm structure should be. Utilizing sails or not could also influence results, as circulations can develop and weaken very quickly, occasionally within a single volume coverage period of time. The interpolation done between elevation slices and the lack of extrapolation from the top data slice can also influence the end result. Look at this example. The 4 cells shown are supposed to be exactly the same, but at different ranges using this VCP. The cell 30 miles away is an accurate representation of the cell. We see the top part of the cell cut off by the cone of silence for the nearest cell. Notice how the more distant storms are reduced in height because the top of the storm just misses the next elevation slice, and there's no extrapolation above the highest data slice. So these cells are the same as the 30-mile cell in reality, but radar displays them to be a little smaller. Take a look at this example. The storm is seen simultaneously by 2 different radars. The left and right images are from radars 30 miles and 80 miles away respectively. All images are for the 0.5 degree slice. Notice the potential difference in threat interpretation if you only had the more distant radar. The right images might lead you to consider a tornado warning, given an environment with favorable deep layer shear, with the lower right image showing rotation, given a radar that's to the northeast scanning to the southwest. But what if this storm was elevated above an inversion? The closer radar better defines what is occurring closer to the ground, in this case, very little rotation. A hail threat perhaps, but likely not a tornado. The mesoanalyst might help when it comes to filling in the information you may be missing, such as this example if you only have the one radar 80 miles away. Another common problem that can frustrate forecasters deals with the orientation of the beam relative to the flow. Velocity images show radial flow, not total flow. This can lead to misinterpretation, sometimes resulting in missed wind events. The image to the right is an example of potential damaging westerly winds associated with a Boeing line segment that is passing well south of the Jacksonville radar. The southward oriented beam would detect minimal along beam flow and thus would show low radial velocities, while trees are being blown down along the path of the Boeing line segment. This can sometimes cause problems accurately assessing boundaries or storm inflow or outflow patterns. One must always keep in mind that velocity images do not reflect total airflow, only a portion of it directed along the radial. Take a moment now to think about how radar data could help you assess near-storm environment, particularly within 50 miles or so of the radar site where you can view lower levels of the atmosphere. Consider features like boundaries, inflow and outflow regions, vertical shear, and how a storm is structured and oriented and how it moves. Let's focus now on several ways that radar can help you evaluate near-storm environment. Storm boundaries and resultant flow on either side can be helpful for assessing changes to low-level shear profiles. The left reflectivity image shows a southward moving boundary from the leading supercell that was moving southward. The environment of subsequent supercells featured northerly low-level flow rather than east to southeasterly low-level flow. As a result, only the first supercell in this train of storms was tornadic, despite all of them displaying impressive mid-level mesocyclones. The right pair of reflectivity and velocity images show a supercell storm interacting with an east to west oriented outflow boundary that was moving slowly southward. If the environment was just marginally favorable for tornadoes, backed inflow and ingestion of greater streamwise vorticity associated with this boundary could locally enhance the tornado threat. Here's an example of a summertime pulse storm event, where intense convergence along a boundary collision supported rapid development of a new severe cell shortly thereafter. In a favorable environment, can this information help the IDSS forecaster provide targeted threat messaging of potential severe storm development prior to the new storm developing? Here's an example of backed and enhanced inflow into a storm of interest. We're looking at storm relative velocity, but we're likely seeing 20 to 25 knots of ground relative flow heading westward through the inflow region of this low-top supercell. The pre-storm photograph shows a fairly small curve, but one that greatly increases in length due to what we're seeing in the inflow region. Changes to low-level shear and SRH at such a small scale will not appear on the SPC mesoanalysis page or in model output. Instead, the mesoanalyst must mentally adjust the local sounding or photograph based on these types of signatures to better understand the actual environment the storm is experiencing and what that could lead to. Not an easy task. The storm ended up producing a tornado in that area. Here's an example of the damage that resulted. Focus on the 4 supercells that will appear in an animation to the right. Which one of them does not show an enhanced inflow region and thus a local max of SRH? Here's the animation. In this case, focus on storm C, which is the one on the lower left part of the image. It does not appear to show much of an enhanced inflow region, even though you're fairly close to the radar site. So storm C is generally associated with a much lower tornado threat. Check out this fascinating animation of a tornadic supercell. Just before the tornado appears in the form of a debris ball in the reflectivity and a TDS signature on the CC plot, we see not only enhanced inflow suggesting an SRH max, but also an interesting southward bulge in the forward flame downdraft rain area just before the tornado occurs. Did this, along with an intense RFD, support continuation of a tornado for multiple radar scans rather than just a brief touchdown? Here's an interesting example of a lone left-moving supercell in northern Florida that produced up to golf ball size hail. Look at the impressive structure on the cross-section. The pre-storm environment featured a straight to slightly cyclonically curved photograph. However, the nearby 0Z Jacksonville sounding showed a slightly anticyclonically curved photograph with negative SRH for the northward moving left mover. The storm occurred before the sounding was available, but the radar imagery clearly suggested an environment supporting the left mover, perhaps even a more anticyclonically curved photograph locally, given how quickly the right mover fell apart. Here's an interesting storm animation that highlights photograph changes across Indiana. Note the dominant left movers in northern Indiana and the dominant right movers in central Indiana. Note how convective mode evolves from linear to large discrete supercells. These changes in time and space reflect changing near-storm environments as highlighted by radar imagery. What does storm orientation tell you about the alignment of shear vectors with height as shown by the photograph? Here we see 4 different supercell alignments from north to south to east to west, each reflecting a different photograph pattern. The photograph would be elongated more north to south for the far left storm and more east to west as you go to the right on this row of storm images, even more northwest to southeast for the far right image. Here's an example of 2 supercells, each oriented slightly differently. The northern one northeast to southwest and the southern one more east to west. What does this suggest about subtle photograph differences between the northern and southern storms? This is not coincidence. Storm structure is responding to the pattern of shear vectors with height as a near-storm environment photograph would show. The right image shows a cluster of pulse severe storms in a summertime weak flow environment. With very little storm relative flow aloft, the photograph would be very short, and the storms appear more circular than elongated. Consider a scenario where you have strong low-level shear with minimal shear above. Surface-based storms would likely convey an orientation representative of the full shear profile. But what if the storms were elevated above the low-level shear? Radar may end up showing very little elongation because it is within a layer of minimal shear. Thus, the lack of storm elongation could be a clue that the storms are elevated rather than surface-based. It's interesting how radar can provide a sense of local area photograph shape and orientation. To the right is a reflectivity image of Hurricane Ivan from 2004, which produced tornadic supercells well northeast of the center. Note how the orientation of the low-top supercells changes from southwest to northeast, east of the storm center, to southeast to northwest, northeast of the storm center. What is causing this difference in orientation? Well, east of the cyclone, the surface flow is likely southerly, veering to southwesterly flow aloft. This would yield a photograph supporting storm orientation more north to south or northeast to southwest. Northeast of the cyclone, surface flow is likely more easterly, veering to southerly aloft, resulting in a different pattern of shear vectors, and thus a hodograph elongated more southeast to northwest, where we indeed see more southeast to northwest storm orientation. Had there been supercells north of the cyclone, a shift to more east-northeast surface flow veering to more southeast aloft likely would have led to more east-to-west oriented supercells. The WSR-88D provides a vertical wind profile for each radar volume scan. This can be helpful for monitoring local area vertical shear. However, it comes with problems. In addition to questionable data quality at times, sometimes you may have very little data at all, although this example shows a gradual increase with time. This often relates to increasing low-level moisture and greater depth of potential targets to support VWP data. In a situation where you have significant environment change from one area to another across the radar coverage area, as suggested in this radar animation, for what area is the Indianapolis VAD wind profile relevant? It likely will not account for small-scale changes to the low-level wind profile that may exist. There are times when we may not fully understand what radar is showing, or its implications to storm or hazard evolution. Here we see a squall line with a mesovortex developing in northern Florida. On the base velocity image, we see a swath of 50 to 60 knot winds in blue ahead of the line, rather than just behind it. The 0Z Jacksonville sounding a few hours later and model guidance indicated winds should be westerly 30 to 35 knots, a short distance above the ground. So what is going on here, and how will it influence the structure of and hazards from this advancing line of storms? Is it an area of locally more intense low-level shear? Is this enhancement created by the line of storms? Are damaging winds occurring at the surface in this area ahead of the line? These questions are hard to answer with any confidence, and that can be quite frustrating. Let's evaluate what is going on within an outer band of convection over southern Georgia that's associated with an inland and weakening tropical cyclone Sally in September of 2020. The mesoanalyst sees a small window of opportunity for tornadoes with low-top supercells along this band. Vertical shear is supportive of storm rotation, but instability is rather weak and shallow, supporting low-top storms. We may need some form of enhancement, either to increase low-level updraft intensity or greater streamwise vorticity within the inflow region. The radar we use will be east-southeast of the storms of interest, scanning toward the west-northwest. Here's an animation of 0.5 degree reflectivity and base velocity images focused on southern Georgia. We see a band of both discrete and linear storms along with some low-level rotational signatures. For this image, let's focus on the northern storm heading towards Waycross, Georgia. Do you see any sign of environment enhancement that could support greater tornado potential? On the velocity image, there appears to be some increase in the outbounds within the inflow region that is highlighted here. This would suggest a relative maximum of SRH, or streamwise vorticity, within the inflow region of the storm of interest. Shortly thereafter, a brief tornado is produced by the storm as it passes just west of Waycross, with some damage resulting. How about this line segment further south in western Charlton County, Georgia? Once again, there appears to be an indication of enhanced inflow, suggesting a small-scale SRH maximum. There's also a small rear inflow notch indicated that becomes more pronounced over time. Shortly thereafter, the storm appears to produce a brief tornado, as indicated by a TDS signature. It is located over an unpopulated area of the county, thus no official damage reports were received. How about the southernmost storm in the line segment, which shows a weak circulation? This small vorticity maximum appears to be on the northern side of a small bowing segment. There is no indication of enhanced inflow in this area compared to the cells further north. No tornado is believed to have occurred here. Let's try a quick springtime supercell case. The vertical wind profile shown to the left appears to be favorable for a mid-level mesocyclone associated with a supercell. Some low-level shear exists, though perhaps at a level that's more favorable for a weaker tornado. On this lowest slice of reflectivity and storm relative velocity, about 4,000 feet above the ground, we see strong rotation that leads to a tornado. Is this data on the velocity image representative of the VWP, or is an enhancement shown? We see an apparent area of enhanced easterly inflow into the storm, which appears well before the TVS indication. Notice a surface observation southeast of the storm indicating a southeast wind. Inflow region wind likely will be more east or east-southeast compared to the more southerly VWP winds. Thus, 0 to 1 kilometer SRH is likely double or triple what the VAD wind profile would suggest, which could locally favor a significant tornado. Here's a summary of key points for this module. The WSR-88D radar can be helpful for assessing near-storm environment changes and the hazards such change could support, but that benefit is typically seen fairly close to the radar, generally within about 50 miles of the radar site. Increasing beam width and height with distance, impact of lapse rate on beam refraction, selection of the VCP or sails used, and how warm or cool a radar is operating can impact the accuracy of the radar data used not only for near-storm environment analysis, but also for storm structure when it comes to warning decisions. The mesoanalyst can assist the radar operator in understanding the impact of these potential issues on a given day. Radar can be helpful for assessing storm boundary interactions, the impact of storm-induced or storm-enhanced inflow or outflow, how vertical wind shear profiles may be changing, and how storm environment may be changing based on changing storm structure, orientation, and motion. A final point to be made for this module. Radar data may not always be helpful for assessing the near-storm environment, unfortunately. It may not detect key features, such as overshooting low-level features a long distance away from the radar. Correct interpretation can be challenging at times. As such, it may be best to incorporate other data sources to the extent possible. You have reached the end of this module. What follows is a short learning assessment. The assessment is not graded, it's simply provided for your benefit. For each question, pause the video as you need to do so to come up with your answer and write it on a piece of paper. Then continue the video to reveal the answer on the next slide. Do this for each question in the assessment. Good luck.